Tonight we float in darkness between galaxies. Not the comfortable darkness of a bedroom after midnight, but a darkness so vast that entire clusters of galaxies drift through it like dust motes in a cathedral. Ahead of you, millions of stars glow in soft rivers of light. Behind you, more galaxies fade into the distance. Everywhere you look, the universe appears calm. And yet something is moving. Not quickly. Not dramatically. Just enough to be strange. Far below, if directions even mean anything out here, a giant spiral galaxy slowly changes course. Nearby, another follows. Then another. Entire collections of galaxies seem to be drifting toward a region of space that should not be affecting them so strongly. It is as though the universe itself is being tugged by an invisible hand. And nobody is entirely sure why. Before we begin following that mysterious pull, there is one small piece of business. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're here, leave a comment telling us your location and local time. It is always fascinating to see where on Earth people are listening from as we wander through places far beyond Earth itself. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You continue drifting. Around you stretches the observable universe, a sphere roughly 93 billion light-years across. Inside it are hundreds of billions of galaxies. Each galaxy contains billions or even trillions of stars. The numbers are so enormous that your mind almost refuses to hold them. Fortunately, the universe does not require permission to be large. That is your first gentle reminder tonight. The cosmos has never been especially concerned with human preferences. If it were, black holes probably would have come with warning labels. As you float through the darkness, you notice something surprising. The galaxies are not simply spreading apart because of cosmic expansion. Many are also moving sideways relative to that expansion. Astronomers call these motions peculiar velocities. The name sounds as though galaxies are wearing unusual hats, but the reality is more interesting. A peculiar velocity is the motion of a galaxy through space relative to the overall expansion of the universe. And some of these motions are enormous. For decades, astronomers carefully measured the positions and speeds of galaxies. They expected gravity to create local movements here and there. Massive galaxy clusters pull on neighboring objects all the time. That part made sense. But when larger surveys became available, a puzzling pattern began to emerge. Huge regions of galaxies appeared to be drifting in roughly the same direction. Not a few galaxies. Not dozens. Thousands. Entire cosmic neighborhoods seemed to share a common motion. Imagine standing beside a calm ocean. The surface looks peaceful. Then you notice every boat, every piece of driftwood, every floating leaf is slowly moving toward the same distant point beyond the horizon. You would immediately suspect a current. Something underneath. Something unseen. That was essentially what astronomers discovered. The galaxies appeared to be riding a cosmic current. The destination of that current became known as the Great Attractor. Even the name feels mysterious. The Great Attractor. It sounds less like a scientific term and more like a title from an unfinished science fiction novel discovered in an observatory basement. Yet the phenomenon is very real. Measurements suggest that our own galaxy, the Milky Way, is participating in this motion. You are moving with it right now. Earth circles the Sun. The Sun orbits the center of the Milky Way. The Milky Way travels through a collection of nearby galaxies called the local group. The local group moves relative to surrounding structures. and all of it appears to be drifting toward a distant gravitational destination, a destination hidden behind one of astronomy's greatest inconveniences: ourselves. The region containing the Great Attractor lies largely behind the dense plane of the Milky Way. Countless stars, clouds of dust, and glowing gas obscure our view. It is rather like trying to identify a mountain while staring through a forest. The obstacle is not the mountain. The obstacle is everything between you and it. This hidden region became known as the zone of avoidance. An excellent name, although it sounds suspiciously like somewhere a tired cat might spend the afternoon. For many years, astronomers could not clearly see what lay beyond it. Yet the gravitational influence remained undeniable. Something massive was there. Very massive. Massive enough to affect the motions of galaxies across hundreds of millions of light years. You watch the surrounding galaxies continue their silent migration. No engines. No explosions. Just gravity. The weakest of the fundamental forces in everyday life, yet the architect of cosmic structure. Gravity shapes planets. Gravity gathers stars. Gravity builds galaxies. Gravity assembles clusters of galaxies. And somewhere ahead, gravity appears to be organizing motions on a scale almost difficult to comprehend. The deeper you look, the stranger it becomes. Because the Great Attractor is not a single object. It is not a giant black hole swallowing the universe. It is not a cosmic vacuum cleaner. Popular imagination often prefers dramatic monsters, but reality tends to be subtler. The mystery lies not in one extraordinary object but in an immense concentration of mass spread across a vast region of space. At least, that is what current evidence suggests. Already, questions begin piling up. How much mass is there? Can we actually see it? Is visible matter enough to explain the observed motions? Could dark matter be involved? And perhaps most intriguingly, what if the Great Attractor is not the end of the story? You continue floating. The galaxies around you resemble islands illuminated by billions of suns. Between them stretch unimaginable voids. Some regions contain almost nothing at all. Others contain structures so enormous that they challenge intuition itself. Human beings once believed the Milky Way was the entire universe. Then we discovered other galaxies. Then clusters. Then superclusters. Then filaments stretching across cosmic distances. Every generation finds itself standing inside a larger reality than the previous one imagined. The Great Attractor emerged from that pattern. A reminder that the map of the cosmos remains unfinished. Somewhere ahead, hidden beyond curtains of dust and stars, lies a region powerful enough to influence our galaxy's motion. We have measured its effects. We have traced its pull. We have even begun identifying the structures responsible. Yet the mystery remains. Because each time astronomers approach the answer, they discover that the universe may be pointing toward something even bigger. And so, carried by the same gravitational current as the Milky Way itself, you drift onward into the darkness, following a pull that began long before humanity existed and may continue long after every star you know has faded away. The darkness around you does not feel empty anymore. Now that you know galaxies are moving together through space, the universe begins to resemble an ocean. Not an ocean of water, but an ocean of gravity, woven across unimaginable distances. You continue drifting through it, carried along with the Milky Way itself. The mystery remains ahead, hidden behind stars and dust. But before you can understand what the Great Attractor might be, you need to understand how humanity learned to measure motion on scales so large that even galaxies become tiny markers on a map. That story begins with a realization that permanently changed our understanding of reality. The universe is expanding. In the early 20th century, astronomers debated the nature of the spiral nebulae visible through powerful telescopes. Some believed they were small objects inside our galaxy. Others suspected they might be entire galaxies of their own. Then observations revealed the astonishing truth. The universe was vastly larger than anyone had imagined. Galaxies existed far beyond the Milky Way. Not dozens, not hundreds, but countless billions. This discovery alone transformed humanity's place in the cosmos. You can imagine standing on a beach believing your island is the entire world, only to discover an endless ocean filled with continents stretching beyond every horizon. That is roughly how dramatic the revelation was. Soon afterward came another surprise. Many galaxies appeared to be moving away from us. The farther away a galaxy was, the faster it seemed to recede. This became one of the foundational observations of modern cosmology. Space itself was expanding, a scientific fact established through decades of observation. The galaxies were not simply flying through pre-existing emptiness. Instead, the fabric of space between them was stretching. Picture raisins embedded in rising bread dough. As the dough expands, every raisin appears to move away from every other raisin. No single raisin sits at the center. The expansion happens everywhere. The universe behaves somewhat similarly. As you float among galaxies, you imagine the cosmic loaf slowly swelling around you. It is perhaps the largest baking project in history. Somewhere, a cosmic chef is probably still waiting for it to cool. But despite this overall expansion, astronomers noticed something unexpected. Galaxies were not moving exactly as predicted. There were deviations. Small at first, then increasingly significant. Certain galaxies appeared to possess extra motions layered atop the expansion. These peculiar velocities hinted at hidden gravitational influences. Imagine standing beside a river. The current flows steadily downstream. Then you notice a leaf drifting sideways toward a point near the bank. Something beneath the surface must be affecting its path. Astronomers began searching for the cosmic equivalent. The challenge was immense. To measure these motions, researchers needed accurate distances to galaxies. And measuring distance across millions of light-years is notoriously difficult. You cannot stretch a tape measure from one galaxy to another. Even if you could, the budget request would likely be denied. Instead, astronomers rely on clever techniques. Certain types of stars behave like cosmic mile markers. Some explode with predictable brightness. Others pulsate in reliable patterns. By comparing how bright these objects appear to how bright they truly are, distances can be estimated. Over decades, increasingly sophisticated surveys produced increasingly detailed maps. The universe slowly revealed its structure. And what a structure it turned out to be. At first glance, you might expect galaxies to be distributed randomly, like scattered grains of sand. Instead, they form a vast cosmic web. Long filaments of galaxies stretch across space. Clusters gather where filaments intersect. Gigantic voids occupy the spaces between. The observable universe resembles an intricate network more than a uniform cloud. A surprising observation is that some of these structures extend for hundreds of millions of light-years. They are among the largest known features in existence. If you could view the entire cosmic web at once, it might resemble a glowing neural network suspended in darkness. The resemblance is only visual. Galaxies are not giant neurons. Still, it is one of those images that lingers in the imagination. As astronomers mapped this web, they began tracking how galaxies moved through it. Patterns emerged. Groups of galaxies were falling toward regions of higher mass. Clusters merged into larger structures. Superclusters formed. Gravity sculpted the architecture of the cosmos. This was expected. What proved unexpected was the scale. The motion suggested that enormous concentrations of matter were influencing galaxies across tremendous distances. One particularly influential clue came from observations of something called the cosmic microwave background. This faint glow fills the universe. It is ancient light released when the cosmos was only about 380,000 years old. Today it surrounds you in every direction, invisible to human eyes but detectable with sensitive instruments. It is often described as the afterglow of the Big Bang, one of the most important pieces of evidence in modern astronomy. When scientists measured this ancient radiation, they discovered a subtle asymmetry. One side appeared slightly warmer than the opposite side. Why? Because the Milky Way itself is moving through space. The difference acts almost like a cosmic headwind. From this effect, astronomers could estimate our galaxy's motion relative to the observable universe. The result was remarkable. The Milky Way is traveling at roughly 600 kilometers per second relative to this ancient background radiation. That is more than 2 million kilometers per hour. Fast enough to circle Earth many times in a single hour. And yet you feel nothing. No rushing wind. No vibration. Only silence. The universe is very good at making extraordinary things seem calm. The measurements confirmed something important. Our galaxy was not merely participating in cosmic expansion. It possessed a substantial, peculiar velocity. Something was pulling. Something massive. Something distant. You continue moving through the cosmic web. Around you, galaxy clusters glow like cities scattered across a dark landscape. Each cluster contains hundreds or thousands of galaxies bound together by gravity. Some are dominated by giant elliptical galaxies. Others contain spirals glittering with newborn stars. Invisible halos of dark matter surround them all. Dark matter itself remains one of astronomy's greatest mysteries. Scientists infer its existence through gravity. Galaxies rotate too quickly for visible matter alone to hold them together. Clusters contain more gravitational influence than their luminous contents can explain. Something unseen appears to contribute most of the mass. We do not yet know exactly what it is. And already the mystery of the Great Attractor begins connecting to deeper mysteries. Because whenever astronomers calculate the mass required to explain large-scale motions, dark matter enters the conversation. Again and again. Like a shadow standing just beyond the edge of the light. The farther you travel, the more interconnected everything becomes. Galaxy motions lead to superclusters. Superclusters lead to dark matter. Dark matter leads to questions about the fundamental composition of the universe itself. The Great Attractor is no longer just a destination. It is becoming a crossroads, a place where many cosmic puzzles appear to meet. Ahead, beyond the obscuring stars of the Milky Way, the gravitational current continues. You can feel it only through its consequences. A subtle drift. A slow migration of galaxies. An invisible influence shaping motions across hundreds of millions of light years. And soon, as the cosmic map grows clearer, you will begin following that current directly, tracing the paths of galaxies as they flow through the universe toward a destination still hidden from view. You follow the current, not through water, not through air, but through spacetime itself. The galaxies around you continue their slow migration across the cosmic web, moving along pathways shaped by gravity over billions of years. Nothing rushes. Nothing hurries. The universe prefers patience. A galaxy can spend hundreds of millions of years traveling toward a destination and still be considered in the early stages of the journey. Out here, deadlines are almost meaningless. You drift beside a spiral galaxy whose stars form graceful arms of pale blue light. Hundreds of billions of suns orbit its center. Trillions of planets may circle those stars. Entire histories could unfold within it. Civilizations could rise and vanish. Oceans could form and dry away. Species could appear, wonder about the cosmos, and disappear again. And through all of it, the galaxy itself would continue drifting along the same gravitational route. The scale is difficult to absorb. A surprising observation about the universe is that its largest structures evolve extraordinarily slowly, while its smallest processes can occur almost instantly. Deep inside an atom, changes happen in fractions of a second. Entire galaxy clusters require billions of years to noticeably rearrange themselves. The cosmos operates on every timescale imaginable. As you continue onward, you begin noticing that galaxies are not scattered randomly through space. They gather into groups. The Milky Way belongs to one such collection called the local group. This group contains more than 50 known galaxies, including the great spiral galaxy known as Andromeda Galaxy. Andromeda is currently approaching the Milky Way. In about 4 to 5 billion years, the two galaxies are expected to merge. Fortunately, galaxies are mostly empty space. Despite involving hundreds of billions of stars, the collision will be less like two cars crashing and more like two vast clouds drifting through one another. Still, it is a dramatic future event. Your descendants, if any exist that far ahead, would witness a night sky transformed beyond recognition. The local group itself is only part of something larger. You continue zooming outward. The local group belongs to a larger collection of galaxy groups and clusters. And those belong to larger structures still. The universe resembles a set of nested patterns. Every time you think you have found the whole picture, another layer appears. This hierarchy eventually leads you toward enormous superclusters spanning hundreds of millions of light years. These are among the largest gravitationally connected structures known. And somewhere within this grand architecture lies the source of the mysterious pull. Astronomers spent decades trying to understand these motions. By measuring galaxy velocities and comparing them to theoretical models, they began tracing invisible gravitational currents through space. The process was somewhat like studying leaves floating in a river. You cannot always see the underwater terrain, but by observing how the leaves move, you can infer what lies beneath. Galaxies became cosmic leaves. Gravity became the riverbed. The Great Attractor became the hidden landscape guiding the flow. You now begin to see the larger pattern. Entire clusters are drifting. Groups of galaxies converge. Massive structures influence one another across distances almost beyond comprehension. This motion is not caused by some cosmic magnet, nor is the universe tipping downhill. Instead, gravity continuously reshapes trajectories, drawing matter toward regions where matter is already concentrated. Gravity is wonderfully self-reinforcing. Matter attracts matter. More matter creates stronger attraction. Stronger attraction gathers more matter. Over billions of years, this feedback builds increasingly large structures. The result is the cosmic web itself. You float along one of its great filaments. Galaxies appear like glowing lanterns suspended on invisible threads stretching into darkness. Between the filaments lie enormous voids. These voids are not entirely empty, but they contain far fewer galaxies than average. Some span hundreds of millions of light years. If you lived inside one, the universe would appear dramatically different. The night sky would contain far fewer neighboring galaxies. Astronomers might struggle to uncover the true scale of the cosmos. Civilizations there could develop entirely different cosmological theories. It is a reminder that perspective matters. Even scientific understanding depends partly on where you happen to be standing, or floating, or drifting through intergalactic space while listening to a bedtime story. As the journey continues, the current becomes clearer. Galaxies ahead seem to flow toward a broad region rather than a single point. This is important. The Great Attractor is often imagined as one object. In reality, observations suggest something more complex. Large-scale gravitational influences arise from entire concentrations of matter spread across immense volumes of space. Clusters, superclusters, dark matter halos, interconnected structures. Together they generate the pull astronomers observe. A scientific fact worth remembering is that gravity travels at the speed of light according to modern physics. When distant masses influence one another, the information about that influence propagates through spacetime itself. Even gravity requires time. Nothing in the universe appears capable of transmitting information instantaneously. This creates an intriguing consequence. The structures influencing our galaxy today are being observed as they existed millions or hundreds of millions of years ago. You never see the universe as it is right now. You only see its past. Every observation is a message delayed by distance. The stars overhead are old photographs. Galaxies are ancient memories. The deeper into space you look, the farther back in time you travel. By the time you observe the region associated with the Great Attractor, you are seeing light that began its journey long before humans built cities, long before recorded history, long before agriculture. The universe arrives by mail, and the delivery times are spectacularly inconvenient. You continue moving. Ahead, the Milky Way's greatest obstacle looms. The plane of our galaxy stretches across your view. Dense clouds of dust block visible light. Countless stars fill the horizon. This brilliant band of starlight creates one of the most beautiful sights in astronomy. It also creates one of its most frustrating blind spots. Behind it lies the region astronomers call the zone of avoidance. Not because nothing exists there. Quite the opposite. The problem is that too much exists in the foreground. Trying to observe beyond it is like attempting to study distant mountains through a brightly lit forest at night. For decades, this obstacle concealed crucial information. Researchers knew something massive lay beyond. The motions of galaxies strongly suggested it. Yet direct observation remained difficult. This uncertainty gave rise to numerous questions. How much mass was actually present? Was visible matter sufficient? How much dark matter contributed? Were hidden galaxy clusters waiting to be discovered? Could the Great Attractor explain all observed motions? Or was it merely one piece of a larger puzzle? These questions lingered. Some have been partially answered. Others remain open today. The farther you travel, the more the mystery expands rather than contracts. That is often the nature of scientific exploration. You begin searching for one explanation and discover 10 new questions. Ahead, beyond the veil of the Milky Way, observations are about to reveal enormous hidden structures. structures larger than many astronomers initially expected. Structures that suggest the Great Attractor may not be the ultimate destination after all. The current continues. The galaxies keep moving. And somewhere beyond the curtain of stars, an even greater mystery waits. The Milky Way now fills half the sky. From Earth, it appears as a beautiful band of pale light arching overhead on a clear night. From here, drifting far beyond our galaxy, it looks very different. It resembles a vast luminous wall. Hundreds of billions of stars crowd together into a brilliant disk. Rivers of gas glow faintly between them. Dark lanes of dust twist across the structure like shadows painted on light itself. Beautiful, ancient, and deeply inconvenient, because directly behind this radiant barrier lies the region that has frustrated astronomers for generations. The zone of avoidance. The name sounds dramatic, almost forbidden, but it refers to something surprisingly simple. When scientists first mapped distant galaxies, they noticed a large area where relatively few galaxies seemed visible. At first glance, it looked as though part of the universe might actually be emptier than expected. But that wasn't the case. The galaxies were there all along. The problem was that the Milky Way stood in the way. Dust clouds absorb visible light. Dense fields of stars overwhelm observations. Looking through the plane of our own galaxy becomes like trying to spot a candle through a forest illuminated by thousands of floodlights. The universe wasn't missing. It was hidden. And hidden things have a habit of becoming mysterious. You continue drifting toward the Great Wall of Starlight. As astronomy advanced, scientists found clever ways to peer through the obstruction. Radio waves helped. Infrared observations helped. X-ray surveys helped. Different wavelengths of light can pass through dust more effectively than visible light. Gradually, the curtain began to lift. The zone of avoidance started revealing its secrets. And those secrets were enormous. One of the most surprising observations in modern astronomy is how often the universe hides its largest structures in places we initially overlook. Entire galaxy clusters remained concealed simply because they sat behind our galactic disk. Once astronomers learned how to see through the obstruction, new structures appeared where blank spaces had once existed. The cosmic map began changing. Again, the story of astronomy is filled with moments like this. Every time humanity develops a better instrument, reality grows larger. Every time a new window opens, the universe becomes more complicated. You move closer. Beyond the stellar curtain, immense collections of galaxies emerge from the darkness. Clusters. Groups. Superclusters. Matter gathered on scales almost beyond imagination. A galaxy cluster is not merely a collection of galaxies. It is an ecosystem. Thousands of galaxies may orbit within a common gravitational field. Hot gas fills the space between them. Invisible dark matter provides much of the cluster's total mass. The entire structure can span millions of light years. Some clusters contain more mass than 1,000 Milky Ways combined. And there are many such clusters. Gravity has been assembling them for billions of years. A scientific fact established through observations is that most of the mass in galaxy clusters appears to be dark matter rather than ordinary matter. The galaxies themselves contribute only part of the total gravitational influence. The rest remains invisible. You cannot see it directly. You detect it through what it does, through how galaxies move, through how light bends, through how matter gathers. Dark matter remains one of the greatest unsolved mysteries in physics. No one has yet identified exactly what it is. Yet its gravitational fingerprints appear everywhere. The closer you look at the Great Attractor region, the more those fingerprints become impossible to ignore. You drift among hidden clusters that astronomers spent decades uncovering. Some of these structures were completely unknown to earlier generations. They existed the entire time. Humanity simply lacked the tools to perceive them. There is something humbling about that. At any given moment, reality contains more than we currently understand. Not because nature is trying to deceive us, but because knowledge arrives gradually. Like dawn, you begin noticing immense gravitational relationships between neighboring structures. Clusters pull on clusters. Superclusters influence surrounding regions. The cosmic web grows denser. The Great Attractor starts to feel less like an object and more like a landscape, a gravitational terrain, a vast valley toward which matter slowly flows. Imagine standing on a continent and asking where all rivers lead. There may be many tributaries, many channels, many streams, yet they gradually converge. The Great Attractor resembles such a convergence point on cosmic scales. Not a single monster waiting in the darkness. A region where gravity from enormous concentrations of matter guides the motion of surrounding galaxies. This realization corrected one popular misconception. For years, some imagined a gigantic black hole hiding beyond the Milky Way. The idea certainly captured attention. A black hole large enough to drag entire galaxy clusters sounds dramatic. The universe occasionally produces dramatic things. But observations do not support that explanation. Even supermassive black holes, despite their incredible masses, cannot account for the observed large-scale motions. The gravitational influence appears distributed across vast structures rather than concentrated in one object. Still, black holes refuse to stay entirely out of the story. Nearly every large galaxy hosts one at its center. The Milky Way contains a supermassive black hole called Sagittarius A star. Its mass equals roughly 4 million suns. That sounds enormous because it is enormous. Yet compared to the mass involved in superclusters, even Sagittarius A asterisk becomes relatively modest. Scale changes everything. A mountain appears gigantic until viewed beside a continent. You continue onward. More hidden structures emerge. The map becomes increasingly detailed. Astronomers identify galaxy concentrations that help explain part of the observed motion. The evidence grows stronger. The Great Attractor is real. Not as a single object, but as a genuine gravitational feature influencing large regions of space. And yet a new mystery begins appearing. The explanation seems incomplete. The numbers do not entirely settle. Some motions remain larger than expected. Some patterns suggest influences extending beyond the structures already identified. It is a familiar feeling in science. You solve one puzzle. The solution reveals another. Like opening a door only to discover a hallway lined with more doors. The Great Attractor was supposed to be the answer. Instead, it starts becoming another question. Because the newly revealed clusters possess enormous mass. Yet evidence increasingly suggests they may not be the final destination of the cosmic flow. Something farther away may be contributing. Something larger. Something beyond the Great Attractor itself. You pause for a moment among the galaxies. Light from trillions of stars surrounds you. Invisible dark matter stretches through the cosmic web. Gravity quietly shapes the trajectories of entire galaxy clusters. Everything feels interconnected. Every structure influences another. Every answer leads outward. The hidden region beyond the Milky Way is no longer entirely hidden. Astronomers have mapped much of it. They have discovered remarkable concentrations of matter. They have uncovered enormous galaxy clusters once concealed by dust and starlight. Yet the current continues. The river of galaxies still flows. And as the map expands beyond the Great Attractor, a startling possibility begins to emerge. The thing pulling galaxies toward itself may also be moving, drawn onward by something even greater waiting in the darkness beyond. The wall of the Milky Way is finally behind you. Ahead stretches one of the most influential regions in the nearby universe, a vast gravitational landscape that astronomers spent decades trying to understand. You have followed the motion of galaxies. You have traced invisible currents through the cosmic web. You have crossed the zone of avoidance. Now you arrive at the heart of the mystery that first drew your attention, the Great Attractor. And what you find is stranger than the name suggests. There is no giant cosmic whirlpool, no universe-sized black hole, no glowing beacon marking the destination. Instead, there is something both less dramatic and more astonishing. There is structure, immense structure. You drift through a realm where galaxy clusters gather in colossal concentrations. Each cluster contains hundreds or thousands of galaxies. Each galaxy contains billions of stars, and all of them are embedded within enormous halos of dark matter whose true nature remains unknown. The scale becomes almost impossible to picture. If the Milky Way were reduced to the size of a grain of sand, some of these structures would still span entire rooms. Human intuition simply did not evolve to visualize hundreds of millions of light years. Fortunately, the universe does not require visualization in order to exist. It carries on being enormous regardless. One of the major structures associated with the Great Attractor is known as the Norma cluster. This cluster sits deep within the region hidden behind the Milky Way and contains an extraordinary amount of mass. When astronomers finally managed to observe it clearly, they realized they had uncovered one of the richest nearby galaxy clusters known. It became a critical piece of the puzzle. A scientific fact established through observation is that the Norma cluster contains hundreds of galaxies bound together by gravity and represents one of the most massive concentrations of matter in our cosmic neighborhood. For a time, discoveries like this seemed to bring the mystery closer to resolution. The hidden mass was being found. The unexplained motions began making more sense. The gravitational current had a source, or at least part of one. You float between giant elliptical galaxies. Unlike elegant spirals, these galaxies appear more like glowing golden spheres. Many contain older stars. Some have experienced countless mergers over billions of years. They are cosmic veterans, ancient survivors of repeated gravitational encounters. Around them drifts hot gas heated to extraordinary temperatures. This gas emits X-rays that reveal the presence of the cluster itself. Without such observations, much of the structure would remain difficult to detect. The universe often announces its secrets in unusual wavelengths. Visible light tells only part of the story. As you move deeper into the region, dark matter becomes increasingly important. In fact, without dark matter, the Great Attractor would make far less sense. The visible galaxies alone cannot account for all the observed gravitational effects. Again and again, calculations point toward unseen mass. Dark matter acts like invisible scaffolding supporting the architecture of the cosmos. Galaxies form within it. Clusters grow around it. The cosmic web itself appears shaped by it. Yet despite decades of effort, physicists still do not know what dark matter actually is. This remains one of the greatest unresolved mysteries in modern science. You can measure its gravitational influence. You can map its distribution. You can watch it shape entire regions of space. But you cannot simply point a telescope at dark matter and observe it directly. It remains frustratingly elusive, like seeing footprints in fresh snow without ever glimpsing the traveler who made them. The deeper you explore, the more impressive the gravitational landscape becomes. Matter gathers into filaments. Clusters sit at intersections. Galaxies stream along preferred pathways. The Great Attractor appears less like a destination and more like a crossroads where enormous structures meet. A surprising observation is that the largest known structures in the universe are not galaxies but networks. The cosmic web spans billions of light-years. Individual galaxies are merely luminous nodes embedded within it. Humanity often imagines galaxies as the primary actors in cosmic history. Yet on the largest scales, they become pieces of something even grander. You begin tracing the motions of nearby galaxy groups. The paths converge. Gravity directs matter inward. The flow resembles rivers feeding a larger basin. This is precisely why the Great Attractor earned its name. Its gravitational influence extends across an enormous volume of space. Even the local group, including the Milky Way, participates in that motion. Right now, every person on Earth is traveling with it. The journey is slow enough to escape everyday notice. Yet the movement is real. The planet beneath every sleeping listener is part of a much larger voyage through the cosmos. There is something strangely comforting about that. Human lives often feel isolated, individual, separate. Yet every person on Earth shares this cosmic motion. We are all passengers aboard the same drifting galaxy, moving together toward a destination discovered only recently in the history of science. You continue observing the region. The evidence is impressive. The Great Attractor clearly contributes to the motions astronomers measure. The hidden clusters are real. The mass concentrations are real. The gravitational influence is real. And yet, the puzzle refuses to close. The farther researchers mapped the surrounding universe, the more another possibility emerged. The flow of galaxies did not appear to stop here. It continued. Subtly. Persistently. Like water crossing one valley on its way toward another. This realization transformed the mystery. The Great Attractor ceased being the final answer. Instead, it became part of a larger story, a larger pattern, a larger gravitational landscape extending far beyond the region originally identified. Imagine hiking toward a mountain visible in the distance. For days it dominates the horizon. You assume it is the destination. Then you reach its summit and discover an entire mountain range beyond it. That is roughly what happened. The Great Attractor turned out to be significant. Extremely significant. But perhaps not ultimate. Astronomers began uncovering evidence that even this enormous concentration of matter might itself be influenced by structures located farther away. Structures so massive that they dwarf many previously known features of the nearby universe. The current you have been following since the beginning of this journey does not end here. It continues beyond the Great Attractor, beyond the hidden clusters, beyond the gravitational crossroads you have finally reached. And waiting farther ahead lies a structure so immense that it forces astronomers to rethink what large truly means. The mystery, rather than shrinking, is about to become larger than ever. You stand, if standing has any meaning in deep space, at what once seemed like the end of the journey. For decades, the Great Attractor occupied a special place in astronomy. It appeared to explain the mysterious motions of galaxies. It provided a destination for the cosmic current. It gave a name to an invisible influence stretching across hundreds of millions of light years. And yet the universe, as it often does, had another surprise prepared. The current does not stop here. You continue drifting beyond the Great Attractor. The galaxy clusters behind you still glow softly in the darkness. Their combined mass remains staggering. Their gravitational pull remains undeniable. But new maps reveal something unexpected. The flow continues onward. The rivers of galaxies seem to be heading toward an even larger destination. The Great Attractor may not be the final basin after all. It may itself be part of a greater watershed. This realization emerged gradually as astronomers improved their surveys of the large-scale universe. Better observations revealed larger patterns, broader structures, more distant concentrations of mass. The cosmic web began looking less like isolated superclusters and more like an interconnected system of enormous gravitational domains. One of the most important discoveries in this effort involved a colossal concentration of galaxies known as the Shapley supercluster. The Shapley supercluster is among the most massive structures in the nearby universe. It contains dozens of rich galaxy clusters and extraordinary amounts of matter spread across an immense volume of space. When astronomers began calculating its influence, they encountered a remarkable possibility. Part of the motion previously attributed solely to the Great Attractor might actually be connected to the gravitational pull of Shapley. In other words, the Great Attractor could itself be moving within a larger gravitational flow. You pause and look outward. The scale becomes almost absurd. A galaxy contains billions of stars. A cluster contains hundreds or thousands of galaxies. A supercluster contains many clusters. And beyond even that, giant interconnected regions influence one another across hundreds of millions of light years. Every time you think you have reached the top layer of cosmic structure, another layer appears. The universe behaves somewhat like an endless nesting doll. Only instead of painted wooden figures, each layer contains enough matter to overwhelm the imagination. A scientific fact established through modern mapping projects is that galaxies are organized into vast structures extending far beyond individual clusters, forming enormous gravitational networks across the observable universe. These networks reveal motions that cannot be understood by examining galaxies in isolation. The cosmos must be viewed as a whole, or at least as much of a whole as humans can observe. You continue toward the deeper current. The galaxies around you become markers in a larger flow pattern. Astronomers sometimes describe these motions using language borrowed from geography and hydrology. Basins, flows, watersheds. The comparisons are surprisingly useful. Just as rainwater eventually drains into larger river systems, galaxies drift along gravitational pathways toward regions of greater mass concentration. The universe contains something resembling cosmic drainage patterns. Only gravity replaces water, and the rivers are hundreds of millions of light-years wide. One surprising observation is that these patterns reveal remarkable order emerging from apparent chaos. When viewed locally, galaxy motions can seem complicated. But when mapped on sufficiently large scales, coherent structures appear. The randomness begins organizing itself into understandable flows. Nature often behaves this way. Complexity on small scales, simplicity on larger ones. You watch galaxies tracing invisible routes through darkness. No signs mark the pathways. No glowing arrows point the way. Yet gravity quietly provides guidance. Over billions of years, matter follows. As researchers studied these flows, another concept emerged: a vast region called Laniakea supercluster. Laniakea means immeasurable heaven in Hawaiian. The name feels appropriate. This immense structure encompasses the Milky Way, the local group, the Great Attractor region, and many surrounding galaxy clusters. Rather than viewing superclusters as isolated islands, Laniakea revealed them as parts of a larger connected system. The discovery offered a new perspective. Instead of asking where individual galaxies belong, astronomers could ask where the flows lead. The answers helped reveal the boundaries of enormous gravitational domains. You are, at this very moment, inside Laniakea. So is Earth. So is every listener quietly resting beneath a night sky somewhere on our small planet. It is a strange thought. People often identify with cities, countries, continents, occasionally planets. Far less often do they introduce themselves as residents of a supercluster spanning hundreds of millions of light years. Though admittedly it would make filling out forms much more difficult. Address line 1 would become a serious challenge. Yet even Laniakea may not represent the final level of structure. That possibility leads directly into one of cosmology's most fascinating questions. How large can cosmic structures become? The observable universe contains filaments stretching across extraordinary distances. Some structures appear so large that they push against expectations derived from cosmological models. Most observations remain consistent with current theories, but occasionally nature presents features that inspire renewed investigation. And investigation, in science, is another word for curiosity made systematic. The deeper you look, the more mysterious the universe becomes. The Great Attractor was once the mystery. Then it became the clue. Then it became part of a larger mystery. Now you begin seeing how scientific understanding evolves. Answers are rarely endpoints. They are stepping stones. Each explanation expands the horizon of what remains unknown. Ahead lies another puzzle entirely. Because even if astronomers successfully map every galaxy cluster, every supercluster, and every gravitational flow, a profound question remains unresolved. Most of the mass responsible for these structures appears to be invisible. Dark matter dominates the gravitational landscape. And even dark matter may not be the whole story. There is something else influencing the cosmos. Something that seems to operate not by pulling matter together, but by pushing the universe apart. Dark energy. A phenomenon so mysterious that it appears to govern the fate of the cosmos while remaining fundamentally unexplained. You continue drifting through the immense architecture of Laniakea. The Great Attractor now lies behind you. The Shapley supercluster glimmers far ahead. The cosmic current stretches onward. And as vast as these structures are, they may represent only the visible contours of a reality whose true composition remains largely hidden in darkness. The farther you travel, the less familiar the universe becomes. Galaxies, once the main characters of the story, now seem almost secondary. Clusters become landmarks. Superclusters become terrain. Gravitational currents flow across distances so vast that even the Great Attractor appears as one feature among many. And yet a deeper realization now emerges from the darkness. Most of what shapes this cosmic landscape is invisible. You drift through a region where galaxies shine like scattered lanterns. Their stars illuminate the darkness. Their gas glows. Their black holes occasionally flare with astonishing energy. These are the parts of the universe that astronomers can directly observe. But according to the best measurements available today, all of that familiar matter accounts for only a small fraction of cosmic reality. a surprisingly small fraction. Everything made of ordinary atoms, stars, planets, dust clouds, oceans, mountains, trees, and every person who has ever lived, appears to represent only about 5% of the universe. 5%. Pause for a moment and let that settle. Imagine reading a 1,000-page book and discovering you understand only 50 pages. Imagine exploring a city while 95% of it remains hidden behind walls. That is roughly the situation modern cosmology faces. The universe appears to be mostly composed of things we do not yet fully understand. The first of these mysteries is dark matter. You have encountered its fingerprints throughout this journey. Around galaxies, inside clusters, throughout the Great Attractor region, along the vast filaments of the cosmic web. Again and again, gravity reveals the presence of more mass than visible matter can account for. A scientific fact supported by multiple independent observations is that galaxies rotate too quickly for their visible contents alone to hold them together. Stars near the outer edges should fly away. Yet they do not. Something unseen provides additional gravitational influence. That invisible component is what scientists call dark matter. The name is straightforward. Perhaps even disappointingly straightforward. It essentially means, there is matter and it is dark. Scientists occasionally display admirable honesty when naming things. Dark matter does not appear to emit light. It does not absorb much light. It does not seem to interact strongly with ordinary matter except through gravity. And despite decades of experiments, its fundamental nature remains unknown. You drift beside a giant galaxy cluster. As light from more distant galaxies passes through the cluster, gravity bends the light's path. This phenomenon, known as gravitational lensing, allows astronomers to map invisible mass. The results are extraordinary. The dark matter often extends far beyond the visible galaxies, like enormous ghostly halos surrounding the structures of the universe. You cannot see the halos directly, yet their effects are unmistakable. The cosmos keeps drawing the same outline. Something is there. Something massive. Something hidden. A surprising observation is that dark matter may have played a crucial role in allowing galaxies to form at all. Shortly after the Big Bang, ordinary matter remained too energetic and diffuse to collapse efficiently. Dark matter may have provided the gravitational framework that helped structure emerge. In a sense, every galaxy you have seen tonight may owe its existence to something we still cannot identify. The universe can be wonderfully ironic. The invisible may have helped create the visible. Yet dark matter is only half of the mystery. Because while gravity pulls matter together, another phenomenon appears to be doing the opposite. You continue moving through the cosmic web. At first, everything seems calm. Clusters gather. Galaxies merge. Gravity shapes structure. Then you zoom outward. Farther. Farther still. Eventually, a strange pattern emerges. The expansion of the universe is accelerating. Not slowing down. Accelerating. This discovery shocked astronomers in the late 20th century. For much of scientific history, researchers assumed gravity should gradually slow cosmic expansion. After all, gravity attracts. If enough matter exists, expansion ought to weaken over time. Instead, observations revealed the opposite. The expansion appears to be speeding up. Something is pushing the universe apart. Or more precisely, something is causing space itself to expand at an accelerating rate. Scientists call this phenomenon dark energy. The name sounds dramatic. The reality is even stranger. Dark energy appears to make up roughly 70% of the universe's total energy content, which means the dominant component of the cosmos remains deeply mysterious. You now find yourself facing an astonishing inventory of reality. About 5% ordinary matter, roughly 27% dark matter, roughly 68% dark energy. The exact numbers continue to be refined, but the overall picture remains consistent. Most of the universe is unknown. You float quietly among galaxies while considering that fact. For centuries, humanity sought to understand the cosmos, and in many ways, we have succeeded beyond the dreams of our ancestors. We know stars are powered by nuclear fusion. We know galaxies exist beyond the Milky Way. We know the universe has evolved over billions of years. We have measured ancient radiation left over from the early cosmos. We have photographed black holes. We have detected gravitational waves. These are extraordinary achievements. Yet when it comes to understanding what most of the universe actually is, the mystery remains open. The situation is almost poetic. Knowledge expands. Mystery expands with it. The horizon never stops moving. You continue through the darkness. Ahead, the cosmic web stretches like luminous threads woven through an invisible framework. Dark matter provides much of the framework. Dark energy influences the expansion of the whole structure. And somewhere within this enormous system, galaxies drift toward attractors, clusters, and superclusters. Every motion reflects hidden forces. Every observation reveals deeper questions. Could dark matter consist of undiscovered particles? Might gravity behave differently on enormous scales? Could dark energy be a property of empty space itself? Or does it hint at entirely new physics waiting beyond current theories? No definitive answers exist yet. Researchers continue investigating. Experiments continue searching. Observatories continue mapping. The mystery remains alive. And perhaps that is one of the most remarkable things about science. The goal is not merely to possess answers. The goal is to learn how reality truly works, even when the answers challenge expectations. You drift onward through a universe dominated by invisible ingredients. The Great Attractor now feels less like an isolated puzzle and more like part of a much larger mystery. Because if most of cosmic reality remains unseen, then perhaps the greatest question is no longer what is pulling galaxies. Perhaps the greater question is what the universe itself is actually made of. And beyond that question waits another, a possibility even more unsettling. What if our current understanding of gravity, matter, and cosmic structure is still incomplete? What if some of the deepest assumptions in cosmology are only the beginning? You continue drifting through the darkness, surrounded by a universe that seems increasingly reluctant to surrender its secrets. The Great Attractor led you to galaxy clusters. The clusters led you to dark matter. Dark matter led you to dark energy. And now, standing at the edge of what modern cosmology confidently knows, you begin encountering the places where confidence gives way to uncertainty. These are not failures of science. Quite the opposite. They are frontiers. The places where observation has traveled slightly ahead of explanation. The places where nature quietly says, there is still more to learn. You float beside a filament of galaxies stretching across hundreds of millions of light years. From here, the cosmic web resembles a vast network of glowing rivers suspended in blackness. Gravity has sculpted this architecture over billions of years. Matter has flowed along invisible pathways. Galaxies have assembled into structures of astonishing scale. Most observations fit remarkably well within the current cosmological model, but not all of them. And those exceptions are where things become interesting. One unresolved mystery involves something astronomers call the Hubble tension. The name sounds almost friendly. A mild disagreement among scientists. Perhaps two cosmologists politely arguing over coffee. In reality, it may point toward something profoundly important. A scientific fact is that astronomers can estimate the expansion rate of the universe using different methods. One method relies on observations of the early universe, particularly the cosmic microwave background. Another relies on measurements of galaxies and exploding stars in the relatively nearby universe. Ideally, both approaches should produce the same answer. Yet they do not. The results differ by more than researchers expected. The discrepancy is not enormous, but it is persistent. And persistent discrepancies have a history of leading to major discoveries. Sometimes they disappear with improved measurements. Sometimes they reveal entirely new physics. At present, nobody knows which possibility will prevail. You continue onward. The darkness feels deeper now. Not threatening, just vast. The kind of vastness that encourages humility. Another mystery emerges from studies of galaxy motions themselves. Certain large-scale flows appear surprisingly coherent across enormous regions of space. Most can be explained within existing models. Yet from time to time, observations inspire debate about whether additional influences might be present. Could unseen structures exist beyond the observable regions we have mapped? Could dark matter behave in unexpected ways? Could subtle aspects of gravity remain undiscovered? Scientists approach such questions carefully. Observation comes first. Speculation follows. That distinction matters. Evidence belongs to science. Possibility belongs to exploration. The two are related but not identical. You drift past a cluster where giant elliptical galaxies glow with ancient starlight. Their stars have orbited for billions of years. Entire civilizations could rise and disappear while a single star slowly circles its galactic center. Cosmic time remains difficult to comprehend. One surprising observation is that some of the largest structures in the universe appear close to the upper limits predicted by cosmological theories. Most fit comfortably within expectations. A few push the boundaries. These structures do not necessarily break our understanding, but they encourage scientists to keep asking questions. Nature rarely rewards complacency. Then there is gravity itself, the familiar force that guided this entire journey. Gravity governs planetary orbits, shapes galaxies, creates black holes, drives the flows that eventually revealed the Great Attractor. And yet gravity remains strangely incomplete. Modern physics contains two immensely successful frameworks. One describes the very large. The other describes the very small. General relativity explains gravity and spacetime with extraordinary accuracy. Quantum mechanics explains particles and fields with equally astonishing success. Both theories work beautifully. The problem is that they do not fit together completely. Somewhere deep beneath observable reality, a more fundamental description may exist. Physicists have spent decades searching for it. Quantum gravity, string theory, loop quantum gravity. Various approaches compete. None has yet achieved definitive confirmation. This remains one of the greatest unsolved problems in science. You pause beside a region of empty space, or what appears empty. Even emptiness has become mysterious. Quantum physics suggests that empty space is not truly empty. Tiny fluctuations continuously emerge and disappear. Particles flicker into existence and vanish again. Vacuum itself possesses properties. Dark energy may even be connected to those properties. Or it may not. The uncertainty remains. The deeper you investigate, the more reality resembles layers beneath layers. Every answer reveals another level. Every level reveals another mystery. And then there are black holes. They have waited patiently in the background of this story. Silent. Watching. Black holes represent one of the strangest consequences of gravity. When enough mass collapses into a sufficiently small region, space-time curves so severely that an event horizon forms. Beyond that boundary, escape becomes impossible. A scientific fact supported by observation is that black holes exist throughout the universe, from stellar remnants to supermassive giants residing in galactic centers. Yet they raise profound unanswered questions. What ultimately happens to information that falls inside? Does information survive? Is it somehow encoded on the horizon? Can black holes eventually evaporate through Hawking radiation? Current theories suggest they can, but the complete story remains unresolved. This is known as the black hole information paradox, one of the most famous mysteries in theoretical physics, and it touches something surprisingly fundamental. Not merely black holes, reality itself. Because if information can truly disappear, some of our deepest assumptions about physics may need revision. The Great Attractor brought you here through a chain of increasingly profound questions. What is pulling galaxies? What creates cosmic structure? What is dark matter? What is dark energy? How does gravity truly work? Does information survive forever? Each mystery opens another, like nested doors stretching into darkness. You continue drifting. Far below, galaxies trace ancient pathways through spacetime. Far above, if directions still matter, the observable universe extends toward horizons no telescope can ever cross. There may be regions forever beyond our view. Not because technology is insufficient, but because light itself has not had enough time to reach us since the beginning of cosmic history. That possibility carries a haunting implication. There may be parts of reality that humanity can never directly observe. Not yet. Not ever. And still we keep looking. We build larger telescopes, more sensitive detectors, better theories. Because curiosity is one of the few forces capable of competing with gravity. Both pull us forward. One moves galaxies. The other moves minds. And as your journey continues beyond the boundaries of established knowledge, the mystery becomes larger than dark matter, larger than black holes, and larger than the Great Attractor itself. The question is no longer merely what exists. The question is whether reality can ever be fully understood at all. The current that carried you toward the Great Attractor has become almost impossible to see now. Not because it vanished, but because your perspective has changed. When you began this journey, the mystery seemed straightforward. Galaxies were moving. Something was pulling them. Find the source and perhaps the puzzle would be solved. Instead, every answer opened another door. The Great Attractor became part of a larger flow. The larger flow pointed towards superclusters. Superclusters revealed dark matter. Dark matter led to dark energy. Dark energy raised questions about the fate of the cosmos. And now, as you drift through the immense darkness between galaxies, The mystery has expanded beyond astronomy itself. It has become philosophical. You float in silence. Far away, entire galaxy clusters shine like scattered embers. Their light began traveling toward you millions of years ago. Some of those photons started their journeys before humans learned to write. Others departed before our species existed at all. Every observation is a glimpse into the past. You never see the universe as it is, only as it was. That simple fact raises one of the deepest questions in science. What exactly is time? A scientific fact established by modern physics is that time is not separate from space. According to general relativity, they form a unified structure called spacetime. Mass and energy curve that structure. Gravity emerges from that curvature. The planets orbit because spacetime itself is shaped. The Great Attractor influences galaxies because spacetime bends around immense concentrations of matter. You have been traveling through that curved geometry the entire night. Yet understanding the mathematics of time is not the same as understanding its nature. Why does time seem to flow in one direction? Why do memories point toward the past rather than the future? Why does the universe possess a history at all? Physicists have powerful theories describing how time behaves. The deeper question of what time truly is remains surprisingly elusive. You continue drifting. The darkness feels peaceful. Not empty. Just quiet. A surprising observation about reality is that nearly every fundamental law of physics works equally well forward and backward in time. The equations themselves often show little preference. Yet your experience clearly does. A broken cup reforms in equations more easily than in kitchens. The universe contains an arrow of time. Why that arrow exists remains an active area of study. Some explanations involve entropy. Some connect to the conditions present shortly after the Big Bang. Others explore deeper possibilities. The investigation continues. And time is only the beginning. Your gaze turns toward the distant galaxies. Each contains billions of stars. Many stars host planets. Many planets may possess oceans, atmospheres, and complex chemistry. Across cosmic history, countless opportunities for life may have existed. Yet the universe remains strangely silent. This mystery has become known as the Fermi paradox. If intelligent life is common, where is everybody? No confirmed evidence of extraterrestrial civilizations has yet been found. The silence itself has become a question. Perhaps intelligent life is rare. Perhaps technological civilizations are short-lived. Perhaps the distances are simply too vast. Or perhaps answers await discoveries not yet made. Nobody knows. The universe keeps its secrets carefully. You drift onward. The galaxies seem smaller now. Not because they have changed. Because your questions have grown larger. Why does anything exist at all? Physics can describe how matter behaves, how stars form, how galaxies evolve, how black holes warp spacetime. Yet the existence of reality itself remains astonishing. Why is there something rather than nothing? Some physicists explore possibilities involving quantum fluctuations. Others investigate multiverse models. Still others suggest the question itself may require reframing. No consensus exists. The mystery remains open. And perhaps it always will. You think again about the Great Attractor. At first it appeared to be a destination. Now it feels more like a symbol, a reminder that hidden influences shape reality at every scale. Galaxies move because of unseen mass. The universe expands because of poorly understood energy. Particles behave according to quantum laws that challenge intuition. Space and time themselves possess properties that would have seemed magical to earlier generations. The deeper you look, the stranger reality becomes, yet also more beautiful. There is something remarkable about a species capable of asking these questions. Human beings evolved on a small rocky planet orbiting an ordinary star. Nothing in evolutionary history required understanding superclusters. Nothing required contemplating cosmic expansion. Nothing required investigating black holes. And yet curiosity emerged. The universe produced creatures capable of wondering about the universe. That fact alone feels extraordinary. Some philosophers have suggested that consciousness may be among the most surprising features of reality. Not because it controls the cosmos. There is no evidence for that. But because it allows the cosmos to become aware of itself, however briefly. A person gazing at the night sky is a tiny fragment of the universe reflecting upon the larger whole. A temporary arrangement of atoms asking where those atoms came from. You, listening now, floating here in imagination among galaxies. You are part of that story, a fleeting moment of awareness within cosmic time. And cosmic time is immense. The Earth is about 4.5 billion years old. The observable universe is about 13.8 billion years old. Stars will continue shining for trillions of years. The last stellar remnants may persist far beyond that. Black holes could survive for unimaginable spans before eventually evaporating. The future stretches so far ahead that ordinary language struggles to describe it. Yet even those vast futures may not be the end. Will the universe expand forever? Will dark energy remain constant? Could unknown physics alter the cosmic trajectory? Might reality undergo transformations beyond current prediction? These questions remain unresolved. The fate of the universe itself is still being investigated. You continue drifting through the darkness. The Great Attractor lies far behind. The Shapley concentration lies somewhere beyond. Galaxies continue their slow migration. Dark matter remains unidentified. Dark energy remains mysterious. Time remains strange. Consciousness remains puzzling. Existence remains astonishing. And perhaps the most profound realization of all is this: the mystery has survived every discovery. Not because knowledge has failed, because knowledge reveals how much more there is to explore. The universe has become more understandable than at any point in human history, and at the same time more mysterious than ever. Ahead lies no final answer, only a horizon. And beyond that horizon, questions still waiting in the dark. You return at last to the question that began everything. What is pulling entire galaxies? The journey has carried you across the cosmic web, past hidden clusters concealed behind the Milky Way, through the Great Attractor, beyond it toward larger structures, into the mysteries of dark matter, dark energy, black holes, and cosmic time itself. And now, standing at the edge of what we currently know, you can finally see the answer in its proper form. The answer is not a single object, not a monster hiding in darkness, not a universe-sized black hole waiting beyond the stars. The answer is a landscape, a vast gravitational terrain shaped by matter distributed across unimaginable distances. Galaxy clusters pull on neighboring clusters. Superclusters influence entire regions. Dark matter provides much of the hidden mass. Gravity sculpts the architecture. The Great Attractor is real. Its influence is measurable. Its effects can be traced. Yet even now, the mystery remains larger than the name itself. Because the Great Attractor is not the end of the story. The cosmic current continues. The map continues. The questions continue. You drift quietly among galaxies. The universe feels calmer now. Not because it has become less mysterious. Because mystery itself has become familiar. A companion rather than an obstacle. Around you, the cosmic web stretches across darkness like luminous threads woven through an invisible framework. Every galaxy follows pathways shaped by gravity. Every cluster participates in larger motions. Every structure belongs to something larger than itself. There is a certain comfort in that realization. Human beings often search for final answers, definitive conclusions, the last page of the book. But the universe rarely offers such endings. Instead, it provides deeper contexts, wider perspectives, larger horizons. The Great Attractor once seemed like an answer. Now it appears as a chapter. One chapter in a story still being written. A scientific fact remains firmly established. The observable universe contains hundreds of billions of galaxies organized into vast structures that evolved over billions of years through the action of gravity. That alone would have astonished nearly every generation that came before ours. And yet the deeper discoveries may be even more remarkable. Most matter appears invisible. Most energy appears mysterious. Black holes challenge our understanding of information. Quantum mechanics challenges intuition. Cosmic expansion continues accelerating. Reality remains richer than our models. The universe has revealed extraordinary truths. It has also preserved extraordinary secrets. You look outward one final time. The galaxies drift in silence. No sound crosses the vacuum. No cosmic narrator announces conclusions. Only light. Ancient light. Light that has traveled for millions and billions of years. Light carrying stories from distant ages. Somewhere, stars are being born. Elsewhere, stars are dying. Black holes are feeding. Galaxies are merging. Planets are forming. Perhaps life is emerging beneath unfamiliar skies. Perhaps civilizations are gazing into their own night skies and wondering about attractors, dark matter, and the fate of the cosmos. The possibility remains unknown. The universe does not rush to explain itself. And perhaps that is why it remains so captivating. Even after centuries of observation, calculation, and discovery, the greatest mysteries endure. What is dark matter? What is dark energy? How did the universe begin? Can gravity and quantum mechanics be united? What lies beyond the observable universe? What is the true nature of time? Will information survive forever? Why does reality exist at all? No complete answers wait at the end of this journey. Only better questions. And maybe that is enough. Because every generation inherits a larger universe than the one before it. The night sky seen by ancient astronomers contains stars. The night sky seen today contains galaxies, black holes, exoplanets, gravitational waves, and the faint afterglow of the Big Bang. Who knows what future observers will add to that list? The horizon continues moving. The mystery continues expanding. The story continues unfolding. And now, as the journey begins to fade into the quiet darkness from which it emerged, you simply drift. No destination. No urgency. Only the slow rhythm of cosmic time. The stars shine around you. The galaxies continue their patient migrations. The Great Attractor remains part of a larger gravitational symphony. And the universe, vast beyond comprehension, carries on. For a little while longer, remain here. Let the scale settle gently around you. Let the questions remain unanswered. Let the mystery breathe. Far away, stars continue burning in their quiet furnaces. Hydrogen becomes helium. Light begins journeys that may last millions of years before reaching another world. Galaxies turn slowly through darkness. Their spiral arms sweep through space with a patience that only cosmic time can teach. At the centers of many of those galaxies, black holes wait. Invisible, silent, shaping the motions of stars while guarding mysteries that physicists still struggle to understand. Between those stars, among clouds of gas and dust, quantum particles appear and disappear in fleeting fluctuations. Tiny events unfold in realms so small they seem disconnected from the grand motions of galaxies. Yet somehow they belong to the same universe, the same story, the same reality. Cosmic time continues flowing. Billions of years pass. Stars are born. Stars fade. Galaxies merge. Clusters evolve. Black holes grow. Then, over incomprehensible spans, even black holes may eventually disappear through the slow whisper of Hawking radiation. Still the universe continues. Still questions remain. And perhaps that is the most beautiful lesson hidden within the mystery of the Great Attractor. We understand more than our ancestors ever dreamed possible. We can map galaxies across vast distances. We can trace the structure of the cosmic web. We can measure ancient light from the early universe. We can detect invisible influences shaping reality itself. Yet beyond every discovery waits another horizon. Beyond every horizon waits another question. The stars remain. The galaxies remain. The black holes remain. The quantum particles continue their strange dance. And cosmic time stretches onward into darkness so deep that even imagination struggles to follow. You drift there peacefully, suspended between knowledge and mystery, between understanding and wonder, between everything humanity has learned and everything still hidden beyond the next horizon. The universe grows quiet. The galaxies become distant lanterns. The stars soften. The darkness deepens. And somewhere, far beyond the Great Attractor, beyond the superclusters, beyond the limits of observation, the deepest secrets remain patiently concealed, waiting,